Hey everybody. What I'd like to do today is talk to you a little bit about population ecology. Now, a population is defined as the number of individuals of a particular species that live in a certain area. And studying populations is really important to our understanding of the world around us. One of the ways that we might quantify a population is to look at its size, simply the number of individuals. Now, it's important to recognize that we usually can't count every single individual in a population. Even the census in a country like the US probably doesn't represent every single individual. And wild animals are not very good at filling out forms, so it might be more difficult to actually find every single one of them. So we have to rely on mechanisms like mark and recapture experiments that I can tell you more about a little bit, um, or estimate other estimation methods to figure out exactly how many individuals might be in a population. But there are other statistics that are also important for a population, and they determine a lot about how those organisms are going to interact with their environment. For example, population density can be really important. Population density is defined as the number of individuals per unit area. A very dense population, like you might have in the human population in New York City, might have very different demands on its environment than a more sparsely populated area like upstate New York. Now, this is same is true for plants, for bacteria, for anything like that. Population density is going to be very, very important. In addition to density, there are a number of other factors that we can look at that control populations, and particularly that control what we call population dynamics, the changes in populations. Some of those factors are what we refer to as vital statistics. Now, we mean vital not as in critical, but literally as in relating to life. The root of vital, vitae, is life. So these are statistics that determine life and death. And most obvious among them is birth rate. Birth rate is simply the number of individuals that are introduced by birth into the population in a certain amount of time. Likewise, we have death rate, the number of individuals that are eliminated through death from that population in a certain amount of time. Now, the other thing that could bring individuals in or out of a population is migration, either immigration with an I in, or emigration with an E exiting the population. Individuals entering or leaving the population can also influence the size of the population. Now, as a population grows, it places different demands on its environment. And one of the things we'd like to look at are the ways that a population could change over time. If we imagine an ideal population in a wonderful place that's the perfect environment, we'd expect that population to grow rather quickly. Now, to give you an idea or a suggestion of perhaps like a little bit of a gross thing to think about, imagine I'm a bacterium that lands on your hamburger. It's perfect. There's more food than I can possibly need in my lifetime. In fact, there's more food than millions and millions and millions and trillions of my descendants could need in their lifetimes. And so what we really have is this panacea, a place where that bacteria can grow in basically an unlimited, at least for the short term, way. That's when we see what we call exponential growth. In exponential growth, the growth rate is tied to simply the population size. Imagine two bunnies. Well, two bunnies are going to produce, say, maybe 20 more bunnies in the next month. But then a month later, when each of those 20 bunnies, or half of those 20 bunnies, tend to have new babies. What do you call baby bunnies? I'm not sure. I'll look this up. But when each of those small bunnies tends to have more, you end up getting, again, a growth. But now there's not just one doe producing a litter. You get 10 does producing a litter. So you're going to have even bigger growth the next month and even bigger growth the next month and so on. That's what you can see in this graph. The population size increases more and more steeply as the population gets bigger and bigger. Same thing with bacteria. 2 make 4, 4 make 8, 8 make 16, 16 make 32, and so on and so forth. So the rate of growth increases as does the population size. Now, that sort of exponential growth is wonderful as long as we have unlimited resources available. But in reality, that's never really the case. Even that hamburger eventually is going to become choked with bacteria. And there are going to be so many bacteria that we start to run into factors that limit population growth. And we'll go into those factors in more detail later. But basically you can imagine some of those factors would be the availability of resources. Resources start to run out. You run out of food, you run out of space, you run out of places to put waste. And with all of those concerns being real and impressing themselves on the population, what you end up getting is something that's called logistic growth. Now, logistics have to do with supply. For a long time, UPS ran a slogan talking about, "We know logistics." The whole idea is it's supply. It's getting enough resources to, in this case, get the population to grow. So with logistic growth, what we see is an initial period of exponential growth when the population is relatively small in comparison to the resources available in the environment. So we get this initial uptick in population. However, at some point, we start to run into these limiting factors. We run out of food, we run out of places to put waste, and so on and so forth. And these factors and others tend to reduce the ability of the population to sustain that exponential growth. In fact, limits on population growth may cause what we call an overshoot, where the population rises and rises beyond a level that's sustainable and then actually crashes before settling at the level that can actually be sustained over time. Now, we refer to this level that can be sustained over time as the carrying capacity. Specifically, the carrying capacity is defined as the maximum number of individuals of one species that an area can support. Every area has its carrying capacity. A lake might have a carrying capacity for trout. A forest might have a carrying capacity for falcons. And in fact, many people have talked about the Earth having a carrying capacity for humans. Now, one of the things about humans is that we tend to find ways to increase the carrying capacity of our environment through better farming practices, through more clever ways of organizing population and resources. However, ultimately, the conclusion is a correct one. There aren't unlimited resources, no matter where we look. And though we found better ways to extract them, at some point, our population is subject to these same controls and will run into limiting factors that may change our population growth over time. Now, one of the other things that we can look at in a population is what we call an age structure. Different populations have different age structures. In other words, we could end up with a lot of young individuals in the population, a lot of middle-aged individuals in the population, a lot of old individuals in the population. It might tell us a lot about the population to think about what ages are represented. For example, in two different countries, you might have a very different picture of the country if one country had a whole bunch of kids aged 5 to 15, and another population had a very small number of children, but a very large number of elderly people. It might tell two different stories of what's going on in those countries. In the same way, if we look at different organisms, we tend to see very different age structures within their populations. And these tend to be sort of characteristic of life habits or life histories among those organisms. Now, we refer to the change in age structure over time, or the survivorship of individuals, as what we call a survivorship curve. If we look at this diagram, and one of the things I'd always encourage you to do in science is to take a look at the labels for the axes you're seeing in your diagram. Here on the y-axis, we have percent survival, and on the x-axis, we have time. So we start off with 100% survival, no matter what sort of organism we're looking at. Obviously, everything is surviving right at the time it's born. Now, over time, you see a change in the amount of survival that we're getting. And these different organisms tend to have drastically different ways of sort of surviving over time. A type 1 organism has a relatively good chance of survival for a long time, up until the point where it gets old and feeble, and then tends to survivorship drops steeply. An organism of type 1 is something that shows a lot of parental care and a lot of chances to sort of look after the young. An example of a type 1 survivorship curve is us. Humans look after their young. And even in societies without advanced medical care or something like this, infant mortality, while steep by our standards, would probably be 40 or 50%, and that's a relatively small infant mortality rate in comparison to much of the rest of nature. Now, if we look at something like a type 2 survivorship curve, what we see is a steady decline over time. This might be because there's some amount of parental care. We're looking after the young to some extent when they can't look after themselves, but there's constantly predatory animals taking a toll on the population and something like this. Things aren't necessarily dying because they're getting old, they're dying because of events in the environment. A curve like this might be something like a rodent. Now, over time, these very few rats in the wild probably live to be old enough to die of old age. In the same way, I look at the turkeys that are outside my house. Every spring, there are a lot of little poults, little young turkeys running around, and as the year goes on, there are fewer and fewer and fewer. They have a hard life. Even though the mother turkeys are looking after them, a lot of them tend to die. And so, yes, we do get a drop in the young turkeys, but over time, there are also things that take their toll on the older ones. Now, the type 3 survivorship curve has a very different shape than what we saw with a human type 1 survivorship curve. In this sort of curve, we see a drastic drop very early in the lifespan of the organism. In other words, the young don't do well. They tend to die off very, very, very quickly. But if you make it to a certain age, then you have a relatively good chance of survival. So we might see this in an organism that doesn't provide a lot of parental care. For example, something like a fish or an insect, or in this case a spider, you tend to get a lot of eggs made. Each one has a very, very small chance of survival. However, if they grow up and become big enough to sort of fend for themselves, then they've got a fighting chance. And so with this sort of survivorship curve, organisms tend to have a ton of offspring. And even though a very small percentage of them may survive to adulthood, that small percentage is still enough to replace the adults that in the population. So none of these survivorship curves necessarily, none of these life histories is necessarily better than another. They're simply different approaches. Humans have a few children and look after them really, really well, and therefore our population will probably either stay the same or grow a little bit depending on the details. Spiders have a ton of children, don't look after them at all, and as a result, you tend to get only a few surviving, but again, those few may be enough to replace the adult population. Now, in a few cases, we see really strange survivorship curves. And one of the things that I want to do is kind of point out one of these, because it's a way that we can see that data really tells us something about an organism, and we can use that data to better understand what's going on. For example, a survivorship curve like this, with stair steps, can be seen in many organisms. Now, this seems initially very odd, but if we think about it, what's causing? Well, there's a precipitous drop in survivorship over time. What that indicates is there are certain periods in the life of the organism that might be very risky. Now, this could be something that's seasonal, there's a predator around, or it could be something that's related to the organism itself. In this case, for example, this might be survivorship of something like a crab. Now, many things that have an exoskeleton have to go through a period of molting. Remember, an exoskeleton confines you. It surrounds your body, and if in order to grow, you have to shed that exoskeleton and develop a new one. And during this time of molting or shedding the exoskeleton, the organism is very subject to predators because it isn't protected by that exoskeleton. So in something like an insect or a crustacean, you might go through these periods where there's a sudden drop in survivorship because the organism simply isn't protected during that time when it's molting. So this stair-step survivorship curve is kind of odd looking, and it actually tells you a lot about how this organism functions. Now, in an upcoming video, we'll take a look at some of the factors that influence all of these vital statistics. I hope that you'll join us then. Take care.